Suppose we look at another example now of a particle with mass in a potential well. So we have a potential well, such as the infinite one-dimensional potential well. We put the particle in this one-dimensional potential well in a pure state. That is some equal linear superposition of the lowest two states of the well, for example. So some amount of this state, n equals 1, and some amount of this state, n equals 2. So here's that linear superposition written out. Well, if we do that in such a superposition, we will actually get an oscillation for the position of this particle. It will oscillate backwards and forwards because of the different time evolution factors buried inside these two wave functions here. So this is what would happen if we put a particle in a pure state that's a linear superposition of the first and second states of this potential well, for example. So that's the behavior of our pure state here. It's oscillating. Suppose instead we take an ensemble of identical potential wells. So here we have a collection of identical potential wells. And we randomly prepare half of them with the particle in the lowest state and half of them with the particle in the second state. So let's randomly put those particles in there. So here we are randomly assigning them to these different possibilities. Statistically, since we don't know which wells are which in this statistical ensemble, at least before performing any measurements, each of these wells is in a mixed state, with 50% probability of being in either the first or the second state. So this concept of a mixed state is quite different from the concept of a pure state where we put a given well into a linear superposition of the first and second states. That's not what we're doing here. We're randomly preparing these different wells either in the first state or in the second state. Now let's evaluate the expectation value, z, of the z position operator for each potential well. In each well, actually, regardless of which state we're in here, z will evaluate to the position of the center of the well, since each of these two wave functions, the first and the second, happens to be equally balanced about the center in this case. Hence, the ensemble average, the average value we would get for looking at the expectation value of the position from all of these different measurements, of the expectation values then from these different wells, is also 0. And there is no oscillation in this state. And again, it would not be correct simply to write this mixed state as a linear combination in this form. It's not behaving like that. This one would be oscillating. This is not oscillating. Let's take another example. Let's suppose that each well is skewed by applying an electric field in the z direction. So here's a skewed well, and we've looked at this problem. The details of it don't matter here, but for example, this might be the first possible state in this skewed well, and this might be the second. So this could be an electron in the well. Now, in this case, the expectation value of z is different for the first and second states of the well. In this case, actually, the electron is slightly more likely to be found towards the left-hand side of the well, and in this case, the electron is actually slightly more likely to be found towards the right. So we would have some z1 as the expectation value position for the first state, a little to the left would be the answer there, and z2 as the expectation value of the position if we were in the second state, which would be a little to the right here of the center. For the pure state, we would still expect oscillation, but for the mixed state, we will not get oscillation. For our mixed state, where we randomly prepare an electron either in the first or second state of these various different wells here, with probabilities P1 and P2 respectively that we'd prepared a given well in the first or the second state, we would still have no oscillation. The ensemble average value of the measured position, however, would now be some generally non-zero number. When we say zero here, we're meaning relative to the centre of the well. This would not just come out to zero, it would come out to some weighted average of these two possibilities. Formally, we could write that out as a sum from j equals 1 to 2, because we've got two different possible states we're working with here, of the probability we're in a given state times the expectation value of the position in that state. That's exactly the same thing as this here. So in our mixed state, we have a formula for figuring out what's the ensemble average, that's the line, of the expectation value of the position. So we can generalize from this idea here. This is position operator in here, and this is only looking at two possible states we might be preparing the quantum mechanical system in. And we expect the ensemble average expectation value for some operator A now, generalizing from just the position operator there, corresponding to some observable quantity, that it can be written in this form. The ensemble average, that's the line, of the expectation value of what we will see for the quantity A, would be given by this kind of formula, just by analogy from that. So we imagine we're looking at j possible different quantum mechanical states in which the system might have been prepared, with probabilities pj for each of those, and we are averaging the expectation value of the position that we would have obtained for each one of those possible different states, j, weighted by its probability, to get the ensemble average. So, for some set of different quantum mechanical state preparations, psi j, with probabilities pj. In considering mixed states, where we are saying that the quantum mechanical state could be in any of a set of different possibilities, psi j, with respect to probabilities pj, the different psi j need not be orthogonal. For example, we could be considering several different polarization states close to one another in angle, perhaps from some fluctuation in time in the precise output polarization of some laser, giving a mixed state of many different possible similar but not identical polarizations. In that case, the psi j's would not be orthogonal. The cases we looked at for the potential well, we did have orthogonal psi j's, but there's no requirement on that when we're talking about mixed states in general.